Howdy! This is your friendly neighborhood physics teacher here, and I'm here to talk about Unit 2 from this semester. Unit 2 was about energy. Reason we did energy is because energy is everything in physics. Energy is everything. Before we get too far into the unit, let's talk about our variables. So at the top of your I think it's the second page of your review, I've given you a list of names. It says variables, unit slash constants, and it's a vector or a scalar. So let's talk about the ones that deal with unit 2. And it's like the first good chunk and then a few sprinkled through. So kinetic energy. Kinetic energy, its variable is Ke. It's energy, so it's measured in joules. Now, I don't believe we talked about it. We might have mentioned it, sort of, but we didn't go too depth into it. Energy is a scalar. It does not matter which direction it's going. It's a losing and gaining of a substance, not that it's going left or right. So it is a scalar. Potential energy is measured in PE, potential energy, so it's variable. Joules, it's still an energy. And it's still a scalar. Again, direction doesn't matter for energy. We have mechanical energy, still a joule, scalar. We have work. Now remember, work and energy are pretty much the exact same thing. Work is just the change of energy. So it's still measured in joules, and it is still a scalar. Next, we have power. Power is measured in watts, and it is still a scalar. It doesn't matter which direction it's going, it's just how powerful it is, an object is. So it doesn't matter which direction it's going. It could be going up or down, it would still be the same amount of power. Next, we have distance in the x direction and distance in the y direction. The variable that represents distance, and I just flat out put power for, it's just p, sorry. So for the x direction, you just represent it with an x. It's distance, so it's measured in meters, and distance is a scalar. Distance itself is a scalar. For the y direction, you just represent a y, measured in meters, and it's still just a scalar. The next is mass. Mass is represented with an m, and it's measured in kilograms, and it is a scalar. Next, we have time. Time is represented with a t. Time is measured in seconds, and time is a scalar. And I know you're like, well, hold on, time can only move one direction, but since it's not really directional, time really isn't directional, it's considered a scalar. Next we have is velocity. Velocity is represented with a v. It is measured in meters per second. Now velocity is a vector. It is a vector. And then we have acceleration due to gravity. That's represented with an ag. It's measured in meters per second squared, but that little thing says constant and units. So what's constant? So acceleration due to gravity is negative 9.8 meters per second squared. That negative means direction, so it's also a vector. So most of these are scalars, and we have a few vectors thrown in there. So now that we know what variables and what units we need, we can now do some practice problems. So let's just start at the beginning. So number 1 says a crane can lift a 500 kilogram mass to the height of 30 meters in 2 minutes. So let's do the guess method. So for our givens, it states that it has a 500 kilogram mass. Our variable for mass is m, and it says it's 500 kilograms. We want kilograms. We're good. There's no converting there. It says our height is 30 So height is in the y direction. So y equals 30 meters. It's distance, meters. We're good. And it says it does it in 2 minutes. That is time. So it's represented with a T in 2 minutes. Uh-oh. Did we want minutes? No, we don't want minutes. We need seconds. So we actually have to do a little bit of converting here. So remember, we don't want minutes. Minutes get shunned to the bottom. We want seconds, though. But for 1 minute, we have 60 seconds. The minutes cancel. And we're left with seconds. That's what we wanted. We wanted seconds. We are good to go. So now we just multiply across the top. And we get 120 seconds. Multiply across the bottom. We just get 1. So therefore, our time equals 120 seconds. So we have meters, or we have mass, we have height, and we have time. And we are looking for work and power. So our unknowns are work and power. So what could be our equations? So let's look at our equations for work and power. Our equation for work is work equals distance times, force, or force times distance. Doesn't matter which way you do it. And then our power is work divided by time. Now remember, we will give you these equations. You don't have to memorize the equations. You just have to know how to manipulate the formulas. So obviously we need work for power. So let's look for work. Let's solve for work first. So work, you need distance times force. So if we look at our givens, we don't have force. So it looks like we need another equation. So let's look at our force equation. Force equals mass times acceleration. We have to think. It's going in the upwards direction. So what force is the crane having to work against? Because work means you're going against something. So what force are you having to go against? If you're going up, what's pulling that object on the crane down? Force of gravity. And if we're using force of gravity, we have to use our acceleration due to gravity. So this just becomes more specific. It's still a force, it's just a very specific force that's affecting the crane. The crane is trying to go up, so the force that's trying to pull it down would be the force of gravity. Now we can use it. So now, and we also have another given. Our acceleration is a negative 9.8 meters per second squared. So our mass is 500. Our acceleration is negative 9.8. So now we just plug that into our handy dandy calculator. And you get a negative 4,900 newtons. So that is our force of gravity. Now remember, we said our work is a scalar. So that negative doesn't matter. That negative doesn't matter. Our distance, it specifically, is in the y direction, because our force of gravity is in the y direction. So our distance is 30. Our force of gravity, we just figured out, is 4,900. So we just multiply those together. And you get 147,000. Remember, your units is joules. And that is your answer for work. Now we need that answer for power. So power is your work, which we just solved for, divided by time. Time was given. We had to do a little bit of work, but pretty much time was given. So our time is in 120 seconds. So we just divide by our seconds, and you get 1,225 watts. And that is our answer. Whoops. Time to jump around here. And there we go. So that's how you find work and power. So you have to think about, so your work is your distance times force. What force are you going against? Which direction are you going? If you have to solve for force, you have that equation, and you can move around there. So now, our next question says, a box pushed at a net force of 200 newtons for a distance of 9 meters. What is the work done on the box? So let's do our givens again. So our givens says a net force, so a force equals 200 newtons. And a distance, so it doesn't give it if it's x or y or anything, just as a distance of 9 meters. And our unknown is the work done. So that's what we're looking for. So our equation, we're looking for work. And work is force times distance. Our force is 200. Our distance is 9. So we just use our handy-dandy calculator. And you will get 1,800 joules. Because work is measured in joules. So that's how my work is done for number 2. Number 3 says, how do you know if a system is breaking the law of conservation of energy? So conservation of energy means all the energy going in, so energy in, so energy going in has to equal all the energy going out. So all the energy going in has to equal all the energy coming out. So if we have, like, let's say a roller coaster here, or here, we'll even do something simple. If we have a car rolling down a ramp, my students love my little sombreros with wheels. So if we have a car going down the ramp, so at the very top, it has potential energy. At the bottom should be 100%. So this was a perfect conservation of energy. It would be 100% potential at the top, and it would be 100% kinetic at the bottom, and they would equal each other. Potential at the top would equal kinetic at the bottom. And that is saying that the law of conservation of energy is not broken. It works. Now, we know that is not true in a real world situation because the car is going to lose energy. It's going to lose energy due to, it's going to lose energy. And it's going to lose it to sound, because it makes a sound when it rolls down. It's going to lose it to friction, because friction is going to affect it. And that friction is going to produce heat. So those are the two main ones. I'm sure there's other ways that the car can lose energy, and that's going out into the system. So therefore, we're not going to have 100% kinetic energy. We might have like 95% kinetic energy. So if you have 100% potential and 100% and not 100% kinetic, that means they do not equal. And if they don't equal, that means it broke the law of conservation of energy. So let's say you're given a data table and you're given all the different energies. You want to make sure all those energies add up to the same number. If they don't, it broke the law of conservation of energy. And most things do, because it releases energy somewhere else. A true system doesn't stay true to the law of conservation of energy. Now, the whole entire world universe does, but just a system doesn't, because it's not a true closed system in a real world situation. Next question. What is the cause of the energy lost with cars braking when brakes are applied, when a car's brake is applied? So again, you have my nice little sombrero with wheels. So you have a car driving, and a car is starting to brake. Now, a couple of things happen when you brake. One, you're slowing down, so the friction between the wheel and the road increase. And also, when you brake, it's called brake pads. What you're doing is you're physically making something, put a stopper, not necessarily on your wheel, but on the your axle, which your wheels are connected to. So you're physically putting a stopper on your axle. And if you have an axle that's spinning and you're putting pressure on there, that's causing friction there. So when you're losing energy again to friction. Losing energy to friction. And that friction, if you rub your hands together long enough, the reason you do that is because it produces heat. So you're losing energy to thermal energy because it's heat. So thermal energy. So you're losing it to heat, thermal energy, and you're doing that by friction. So you're losing this energy because of friction. Next question. Which process of heat transfer is through direct contact? So direct contact, that means the two objects have to be touching. Direct contact. So the two objects have to be touching. So through direct contact, that will be through conduction. Now, which process of thermal energy is through fluid motion? So remember, that's dealing when particles are moving around and they're going around for some source. So you have some type of heat source. You have some type of heat source, and it causes the objects to rise. They cool off. So they cool off. Can't spell. And so they sink back down. They heat up. And then they go back up, cool off, come back down, and you get this nice little rotating pattern here. So it's just kind of rotating, get that nice little rotating pattern. And that is called convection. Remember, we talked about boiling water, and also convection is how clouds are formed and how storms are formed. So that's convection. The next one, it says, which process of heat transfer uses electromagnetic waves and need no medium? So if you notice, your convection, there has to be something to cause it. So conduction physically has to be touching. So there's two things of matter touching. So there has to be a medium. If it's the wind or if it's solid, liquid, there has to be some type of medium to touch to make that heat flow. Convection, there has to be, it's usually a fluid, so it's a liquid or a gas, and particles have to touch because the heat, this particle touches this particle touches this particle, so they're physically touching when they bump into each other to transfer that heat. Now, the one that does radiation, so the big thing is you think about your lovely little sun. The sun produces electromagnetic waves. So you can think about sun. Another thing you can think about is fire. Flames produce electromagnetic waves also. And that is radiation. You talk about like radiating outward. Radiation. And y'all know I can't spell, so yeah. So that's radiation. So there's no medium needed. Because if you think about it, how does the sun heat up the earth? It goes through space. There's no particles like a dense case of particles in space. So there is no medium in space. Heat will, so it can radiate outward. So that's radiation. Which process of heat transfer, oh, I already read that one. What type of heat transfer happens when you hold an ice cube? So looking back here, so you're holding an ice cube. So what are you doing to an ice cube? You're touching it. You're holding the ice cube. The ice cube is touching your hand. So therefore, since it's touching, the answer is conduction. Conduction transfers your hot hand, your heat, to the ice cube and causes it to melt. Number 9 is the big one. It has the different roller coaster, but it kind of hits all kinds of math and conceptual with it. So number 9 says a 100-kilogram roller coaster comes over the first hill. Assume the roller coaster is frictionless. The height of the first hill is 20 meters. Fill in the chart. So the height, so it kind of gives us our givens. So it gives us our height of the first hill. So it gives us a height of 20 meters for the first hill. And then it says hill B is half height. So then it gives us the height of the second hill, which is 10. And then if you look at your picture, C is 0 height. But I kind of have that in the table right below that. So height is given, so it's either 20, 10 meters, or 0 meters, just according at one point you're talking about. Also gave you the mass. The mass is 100 kilograms. And it's asking for what is potential, kinetic, total, and velocity. So we're going to kind of break it up into hill A, hill B, and then C. I can't really call it a hill because it's not really a hill. So C. And we're going to break it apart. So what is the potential energy of hill A? So our potential energy equation is potential energy equals, oops, if I actually put an equal sign, equals mass times acceleration due to gravity times height. And this is our potential energy due to gravity. We know that's potential due to gravity because it has some height. So I know y'all were saying, a lot of my students were saying to memorize it is Peg Maggie. Just go for it. So we're looking for our potential energy. So our mass is 100. Acceleration to gravity is 9.8. Our height is 20 for hill 1. So now you just plug that into your calculator. So you would do 100 times 9.8 times 20, and you would get a really big number. So 19,600, and it's joules because it's potential energy. If you're going to do the potential energy for hill B, if you're going to do the potential energy for hill B, your mass is still 100. Acceleration due to gravity, you're still on Earth, so it's still 9.8. Just your height is now 10. So you do the same thing, 100 times 9.8 times 10, and you just get 9,800 joules. And if you do the potential energy at C, your mass is still 100, acceleration to gravity is still 9.8, but you have no height. So your height is 0. Nothing like for jumping around. Your height is 0. So 0 times anything is 0. So you have your potential energy there. Now let's do our kinetic energy. Our kinetic energy is 1/2 mv squared. Is 1/2 mv squared. So for the first hill, we have 1/2. Our mass is 0. Now on the first hill, you're not really moving there on the first hill. You're not really moving there on the first hill. So your velocity would just be 0. So your velocity would just be 0. So your kinetic energy is 0 joules. And we don't necessarily know the velocity for the other one, so we have to hold off on to kinetic energy just right quick. But we can figure out our mechanical energy, or our total energy. Total energy and mechanical energy are the same thing. Mechanical energy is just your potential energy plus your kinetic energy. So in this case, our potential energy, it was this. Our kinetic energy is 0. So our mechanical energy is just that. What's so special about mechanical energy, or total energy? It does not change. So our mechanical energy will be this all the way through. So it'll be this all the way through. So that's our mechanical energy. So once you figure out the first one, you can just drop it all the way down. And how we can figure out our kinetic energy is you're using this exact same equation. You're using this equation to find our kinetic energy equation. Erase. To find our kinetic energy. So we have mechanical energy equals potential energy plus kinetic energy. We know our mechanical energy. We know our potential energy. So we can solve for our kinetic energy. You just subtract, and what you do to one side, you got to do to the other. So our kinetic energy would equal, when we use our handy dandy calculator, would just give you that, which kind of makes sense, right? Because it's halfway through. So, and just to double check to make sure we did this right, if you're using the mechanical energy equals potential energy plus kinetic energy, it's just that plus that. And that gives you that. So we're doing good. All our maths are lining up. So again, we would use this equation, mechanical energy equals potential energy plus kinetic energy. Our mechanical energy does not change. Our potential energy is 0. So our kinetic energy has to be this. And again, you can check mathematically by using this equation, and you can see that it does add up. Now, let's look at this. So our potential is 0. Our potential is 196,000 joules for hill A, and our kinetic is 0. It flips for C because we've said it's frictionless, it's a closed circuit, so potential at the top equals our kinetic at the bottom. Potential at the top equals our kinetic at the bottom. There we go. Now we can figure out our velocity. Our velocity, we would have to use our kinetic equation. Kinetic equals 1/2 mv squared. Our first one, we know that our velocity is 0 because our kinetic energy is 0. So we kind of already knew that. So we know that our velocity is 0 because it's at the very top and it's not moving at the very top. Now for hill B, it is moving. It's kind of going, it's moving over the hill. Our kinetic energy is 9,800. 1/2. Our mass is 100. We're working for velocity. So let's go ahead and do 1/2 times 100, so that gives you 50. We need to get velocity by itself. They're being multiplied. The opposite of multiply is divide. So you get v squared equals 196. We have to get rid of that squared. The opposite of squared is square root. So we do the square root of our answer, and we get 14. 14 meters per second. And we do the same thing with this one here. So we use the exact same equation. Our kinetic energy is the whole entire energy now, because it's 100% kinetic energy. Again, we simplify it. We need v by itself, so the opposite of multiply is divide. And so you get divided by 50, and you get 392. To get rid of squared, you square root. So you square root 392, and you get 19.80 meters per second. So that's kind of your chart. So that uses your kinetic energy equation, uses your mechanical energy equation, and it uses your potential energy equation. And we can also use it to kind of talk about energy. So if we're making our roller coaster, so we have hill 1, hill 2, hill 3, and kind of going off to La La Land. So these hills, even though I didn't draw it very well, these hills should be the same height. I did not mean to do that. So these are the same height. So they're the same height. So this would be 100% potential. 100% potential. As it's going down, it's turning into kinetic. And that becomes 100% kinetic. 100% kinetic. 100% kinetic. As it's going up, it's turning into potential. Turning into kinetic. Turning into potential. But it's not quite all potential. There's still some kinetic there. So it's potential and kinetic here, because it hasn't gotten all the way to the top, but it's going back to kinetic. Now, going up here to potential, it can only go up to here. Once it goes up to here, it'll just come right back down. It'll come right back down going to kinetic, because it cannot make more energy. So it can't actually go any higher without any help. So if it's just purely running on the energy it gives it, it can't get any higher than the height it started at. So that answers number 7. What is the energy transfer of the roller coaster? Number 8. What is the energy transfer of the skater? Kind of the same things. We have the skater. So up here would be potential energy. Potential energy. Down here will be kinetic energy. And so like right here, it'd be potential and kinetic. Here would be potential and kinetic. It'd be 50-50. So if it's 100% here, 100%, 100%, 100%, it's 50%, 50%, 50%, 50%. And then, of course, if like it was here, it'd be 25-70, and so it's a constant motion here. For the skater, kind of very similar to the roller coaster. Here I have, look at your Miss Frizzle question, your Shazam question, and your Boss Baby question from your second test. Again, I would look at the whole test if I were you. But specifically, those 3 questions. So let's look at that real quick. Let's look at the Boss Baby question. So on the Boss Baby question, it states, rockabye baby on the treetop. When the wind blows, the cradle will rock. Tim so lovingly put 13.25 kilogram. So that's our mass, 13.25 kilogram. Boss baby in the treetop. When the bough breaks, the cradle will fall, and it will fall 17.95 meters. So that is our height. And down will come Boss Baby, cradle and all. Boss Baby had blank joules of potential energy. We are looking for potential energy. So our equation that we're going to use is potential energy. Again, we will give you the equations. You just need to know how to, like, what the variables are. So PE equals MAGY. So we're looking for PE. Our mass is given. Acceleration due to gravity is just 9.8, and our height is 17.95. You just plug that into your calculator. So 13.25 times 9.8 times 17.95. So your potential energy is 2,330.81 joules. So that's your potential energy. The next question was the Miss Frizzle question, or the Magic School Bus question. It says the Magic School Bus breaks down and Miss Frizzle has to apply a force of 1,360 newtons to move the Magic School Bus 17.67 meters. Miss Frizzle does blank joules of work. So let's do our givens. So our givens, it gave us force. So it gave us a force of 1360 newtons, and it gave us a distance of 17.67 meters. And we're looking for work. So our equation would just be work equals force times distance. So you can just multiply our two givens together. So times 17.67. And you get 24,031.20 joules. There we go. And then it also talks about the Shazam question. It says Shazam has a mass of 99,500 grams of solid muscle. Shazam flies in the air at a velocity of 37.8 meters per second, and has blank joules of kinetic energy. Whew, those numbers are big. So let's do our givens. So it gave us mass, and our mass is 99,000 grams. Ding, 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 ding. Things should be going off right now. We do not like grams. So we're going to have to convert it. And then the velocity is 23, 23, erase, come on. Okay, 37.8 meters per second. So we want meters per second, we just don't want grams. So if you remember, grams is a base. We want kilograms. So that's, kilograms is 3, so that gives us a -3. So we're going to move the decimal 1, 2, 3 to the left, because we're negative is telling us to make it smaller. So our new mass that we're going to use is 99.50 kilograms. So that is the mass we're going to use. Our unknown, we're looking for kilograms. The equation we're going to use is just our kilograms equals 1/2 mv squared. So 1/2, our mass, we just converted, so it gives us 99.50 kilograms, and our velocity is fine. We can just use that as is. Do not forget to square it. You can just plug that in your calculator. So you do 1/2 times 99.5 times this horrible number, and I'll make sure you put that in parentheses so you actually know you're just squaring that number, and you get an awfully big number, and that's okay. I'm not even going to try to say the number, I'm just writing it down. Joules. If it's a number that big, let's put that into scientific notation. We're going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. And that'll give you 2.72 times 10 to the 8 joules. So that is your kinetic energy. So there we go. That is part 2 of your review. Again, I would highly suggest you to look at the whole entire Unit 2 test. You never know when those questions might reappear. Hopefully have a wonderful day and happy studying. Bye.